Hi, welcome back to the next video in the IB Math AA Higher Level Calculus series. Today, I'll be looking at limits. Limits are somewhat tricky in the syllabus because there's so many different ways to solve them, but today I'll be looking at every single method of solving limits and presenting them all so that you know how to do them if they turn up in an exam. So let's get right into it. So what are limits, first of all? So they're just the value that a function approaches as the x coordinate approaches a certain value. So what we're looking for is what f of x approaches as x approaches a value. So take this function right here, 1 over x. So here, as x approaches 0, we can see that this part, this half right here, goes to negative infinity. So we say that the left approach, or the negative approach, is negative infinity, and the positive approach is positive infinity. So that means that because these two are in opposite directions, no actual limit exists. So both limits from the left and the right must be converging onto a certain point, and that's the official definition of a limit. So if this one right over here was flipped so that it's like this, then both of them would approach positive infinity, so then we'd have a limit at positive infinity. So that's basically what that means. And this is the notation for it right over here. So a is the value that you're approaching, so in this case it would be 0. F of x is the function, so here it's just 1 over x. And L is the value, so if we're saying this right up here, then it's infinity. So there's many ways to solve limits, and as you can see by this, it can get quite complicated. So let's just take a look at every single one of these methods, because the only thing that you need to know here is computation. So there's different forms. One is where b is by 0. So that's basically a limit that has a real number at the top and then a really small number at the bottom that we call 0, but it can be positive 0 or negative 0, which you've probably learned. 0 can't have a sign, but in this case it's a really small number that either has a positive or negative sign. Then we have directly evaluatable limits, so it's literally you just substitute a in and we get b. That's the easiest kind, and that's also the one you're least likely to see on exams because it's too easy. Then we have 0 by 0 or infinity by infinity limits, and these are called indeterminate limits. And basically what you've got to do here is use something like factorization or L'Hopital's rule. And then d is a factoring limit, so it's different from this because it doesn't necessarily need to be 0 by 0, but you can use the same techniques here, but it's usually easier not to factor these. Then we have conjugate limits, where you multiply by the conjugate, and then we have trig limits. So for this, there's a little theorem I'd like to introduce when it comes to that to make it a little bit easier to avoid trig identities. But yeah, you can use trig identities essentially. So let's first look at the easiest type of limit, direct evaluation. So when this function right over here, 3x squared minus 5x plus 1, approaches 2, we can literally just try and find the value of f of 2 to find the limit as x approaches 2. So if we substitute and we get 3 times 2 squared minus 5 times 2 plus 1, which gives us 12 minus 10 plus 1, which happens to be 3. So if we get a real number after literally just substituting, that means we found our limit and it's done. So always just try and substitute in the random kind of number, that this number right over here first, and see if you get lucky. Now, if you don't, it's probably one of these types of limits. So the first is called a b over 0 limit, where b is a real number, and the bottom is 0. So it's not actually 0, it's a very small or positive or a negative. So for instance, let's take this limit as x approaches 1 of 5 over x minus 1. So as x gets closer and closer to 1, the denominator gets closer and closer to 0. So basically, if we approach from numbers bigger than 1, so like 1.1 minus 1, we get closer and closer to 0, but the value is positive. So if we have 1.1, we have 1.1 minus 1, so that's 0.1. If we have 1.001, then it's 1.001 minus 1, which is 0.001. So it's a small positive number. And so when we have 5 divided by a really small positive number, we get positive infinity. When we do it from the left now, just by the exact opposite principle, we get a really small negative number. And when we divide a positive by a negative, we get negative infinity. And so, because the left-handed limit does not equal the right-handed limit, one gives you positive infinity and the other gives you negative infinity, we can say this one right here does not have a limit. And then the third is a 0 by 0 limit. This is called an indeterminate, and it's very, very common in exams. So, for example, this one right over here gives you 0 by 0, because if you do 2 square minus 4, that gives you 0, because that's 4 minus 4, and 2 minus 2, that is 0, so we have 0 by 0. If we have infinity by infinity, the same thing can happen. So if we had infinity here instead, and we had infinity squared minus 4 divided by infinity minus 2, that is infinity by infinity, so we can use the same principle again. So what we do here is we differentiate the numerators, so we take the derivative of x squared minus 4, and we find that that is 2x. Then we differentiate the denominator, so we take the derivative of x minus 2, which is 1, which gives us 2x by 1. And then we just substitute 2 like we did right over here in order to get 2 times 2, which is 4. Keep in mind, this is called L'Hopital's rule, and it's given in the formula booklet, I believe, but it only works when you have either 0 by 0 or infinity by infinity when you try and directly substitute. It won't work, for instance, for this type of case. Next, we have a factorization limit. So that's when you have two polynomials, one in the top and one in the bottom. And what we can do here is take the limit as x approaches 3 by factoring. So if we literally directly try and substitute, we once again get a 0 by 0 case. We get 9 minus 9 over 3 minus 3, which is 0 by 0. But we know from the difference of two squares that x squared minus 9 can be written as x plus 3 times x minus 3, which allows us then to cancel these x minus 3's and leaves us with only an x plus 3. So now, once again, we substitute the 3 into the x plus 3, and we get 6. Next, there's a conjugate limit. So this is when we have a square root. You can generally assume it's a conjugate limit. And for instance, for root x minus 2 by x minus 4, what we do here is we take the conjugate of the numerator, and here the conjugate of root x minus 2 is just root x plus 2, so we just swap the sign between the variable and the thing and the number from minus to plus, and then we multiply it by both the numerator and the denominator. So here we take that, this is just essentially 1, it's a really weird way of writing 1, and we multiply that over both the numerator and the denominator. And when we do that, given our a plus b times a minus b identity that we used for factorizing, if we reverse that now, so if we use that to expand, we get root x squared minus 2 squared, which gives us x minus 4 divided by x minus 4 times root x plus 2. And then these x minus 4's cancel out, giving us 1 over square root of x plus 2. And once again, just like we do with all the other ones, the final step, we substitute in 4, and we get 1 over square root 4 plus 2, and square root 4 is just 2, so it's 1 over 4 is the final answer. And lastly, what I think is the hardest type of limit to solve is a squeeze limit, at least in IB. And this is basically when we have trigonometric functions. So for instance, if we have this function x squared times sine 1 over x, and we need to find the limit as this approaches 0. If we tried substituting 0 directly, we'd get sine 1 over 0, and 1 over 0 doesn't exist. So we can't do that. So what we do basically is we know the bounds of sine x is -1 is the lower bound and 1 is the upper bound. So if we let u equal 1 over x, we know sine u is bounded by these. So sine 1 over x must also be bounded by -1 at the lower end and 1 at the upper end. And now when we just multiply x squared right over here by in this entire inequality to get this function here. We get negative x squared less than or equal to x squared sine 1 over x less than or equal to x squared, because we're just multiplying this entire thing by x squared here. And so if we take the limit of the bottom and the limit of the top, and they're equal, then we have the limit of the middle function. And that's what's called the squeeze theorem. I don't think that's explicitly part of the IB curriculum, but you are expected to solve limits with it. So you don't need to know that it's called the squeeze theorem. You just need to familiarize yourself with this sort of procedure. And as you can see here, if we substitute 0 into negative x squared, we get 0. And if we substitute 0 into x squared, we get 0, which means that this entire limit, which is sandwiched between these two inequalities, must also be 0. So yeah, that's pretty much the entire topic of limits that you'll need to know for the final IB exam. As you can see, there isn't a lot conceptually, but there's just so many methods of trying to figure out these limits that it can get really tough. So practicing evaluating different types of limits is your best bet for the finals. I hope you found this video helpful, and thank you so much for watching. And yeah, stay tuned for the next one.